Okay, we're at the last topic. So 10F and 10G, we're looking at the amount of energy you get from food and how you measure it. Symbol for energy is confusing. They're all referring to the joules or kilojoules, but we could use Q as our symbol, or Edrolo uses E sometimes. In physics, they use a capital Q. Change in enthalpy that we've looked at before is also the amount of energy. So all of these different symbols are talking about the amount of joules. So there's 4 different areas that we're going to look at. If you're given a table and we're looking at food, so if you know the percentage of carbohydrates, proteins, fats in a type of food, you can look up the data booklet and find how much energy you would get, how many kilojoules for every gram of carbohydrate. And if you know how many grams of carbohydrate in 100 grams of the food, then you can work out how many kilojoules you would get if you ate the bread because of the carbohydrates. So that's the first thing that we're going to look at. The second thing we're going to look at is using either combustion reactions or just the change in enthalpy itself, and relating the number of moles that you're given to the kilojoules you get in a combustion reaction from a change in enthalpy. So this means that you have 2,860 kilojoules for every 1 mole. So if you had half a mole, you'd have half that. So we're just using a ratio for this. This is looking at what we did in Unit 3 right at the beginning, where we had fuels and we burnt the fuel and then trapped the heat in water, and we used the specific heat capacity of water and this equation to work out the amount of energy, joules, that was trapped in the water. Measured the temperature rise of the water and knew the mass of the water. And the assumption was that all of the heat was going into the water. That's not correct. So this is inaccurate. So therefore we're going to use these bomb calorimeters where the heat is given to the water, which is all the way around it and it's not being lost. There's a lot of equations where we're looking at energy. So I'm going to use Q for all of them because they all generally come out in joules. This one is using electricity, and once we calibrate a calorimeter, we can use calibration factor and the temperature rise for the calorimeter to work out the joules for our food. So you kind of need to be able to use the different equations. So there's 4 different ways of finding the energy. We'll look again at the first one. Ultimately, you want to know how many kilojoules for every gram of food if you've got something like bread, or if you've got a pure food like glucose, you could work out how many kilojoules per mole. So the first one is looking at mixtures like bread, and we use the kilojoules per gram for proteins, carbohydrates and lipids that are found in the data booklet, and then you can work out the energy in your food due to each of these, and then overall the energy from if you ate bread. So the second one is using our equations, like I said. So a ratio. So once you've got a balanced reaction, we can relate the number of moles using a ratio, what we want, what we've got, and how those things go together. And we can also relate any of these to the energy as well. So if we wanted the energy and we had a set number of moles, so if we had half a mole, that's what we had. We know that we have 2,860 kilojoules for 1 mole from our reaction. So we can just take this over the other side, the moles will cancel, and we would have half of that. So there are 2 ways of working out energy, given tables and a combustion reaction. The next 2 are if we did experiment, so like the picture said, if we use the specific heat capacity of water, 4.18 joules per gram per degree, and we heat the water with that amount of fuel, like food. So burning the food, if we have a set amount of water and it goes up a certain temperature, these will cancel and you'll be left with the energy that was trapped in the water from the food being burnt. I'll ignore this. I thought I'd got rid of this. So that's inaccurate because we're losing heat from the container. So the next one is using the bomb calorimeter. So there's two steps to this. We would need to work out the energy. We can't use the specific heat capacity of water. We need to calculate the energy you need to heat for every degree that the calorimeter goes up. So we have to calibrate it first. So we need to add a certain amount of energy that we know, a set amount of energy. So the first method is we can use electricity to add this energy and then measure the temperature rise. When we add the electricity, we're going to work out the joules that we added, and we measure the temperature rise to work out the joules per degree. The other way of doing it is like our reaction, where we can add a set amount of energy if we have a set number of moles reacting in the calorimeter, and then we can work out the amount of energy for each degree. So we have to calibrate it, so we need to know how many joules it takes to heat the calorimeter by a degree. This is more information on the electricity one. So if we put electricity into the calorimeter, if we measure the voltage, the current and the time in those units, then voltage, current and time is joules. And then we measure the initial and final temperature, and we can work out how many degrees we added of that number of joules. So we can work out how many joules it took to heat the calorimeter by 1 degree. Sometimes we have to do a graph too, so that we get the final temperature to be accurate. The other one is the reaction, which is like the first one, but we're using it to calibrate a calorimeter. So we can do a reaction where we know the kilojoules per mole, and then we can, for however many mole we burn in there, we can work out how many kilojoules must have been released and look at the temperature rise. So once we've got this calibration factor, we can use it to work out the amount of energy that you would get for a particular food. So these are the two techniques, calibrating it. So the calibration factor is how many joules per degree, and it's very similar to the specific heat capacity. So we know how many joules to heat it by 1 degree. The reason that the grams are missing is because when we calibrate it and when we use it, we're going to use the same amount of water in our bomb calorimeter, so we can leave the grams off. Whereas when we're using this one, we can use this equation for any number of grams of water, and so we need to know the number of grams. Otherwise, the calibration factor and the specific heat capacity are basically the same idea. So it's once you know how many joules it takes to heat your bomb calorimeter, then we do our reaction with food, and then we can work out how many joules our food has released. So this is just going on a bit more about the working out the energy of the food. With the bomb calorimeter, they cancel. So once you know the energy for the food, then we can work out how many, if we've got a certain amount of energy or a certain mass of food that we combusted, we can turn that into the kilojoules we would have gotten for 1 gram, kilojoules per gram of a mass of food. We need to look at the errors. So when you calibrate the calorimeter, If the container is not insulated, heat is lost, the change in temperature would be lower. So the calibration factor would be higher. So if you're losing the amount of energy that it's gone up is lower than it should have been, which makes your calibration factor higher than it should be. This means more energy would be needed to give the same temperature. Okay. If it's calibrated with 100 mils of water, then 100 mils of water must be used in the reaction. If less is used, then the heat produced only has to change the volume of the temperature of a smaller volume. So there will be a larger change in temperature than there should have been, so more energy would be calculated to have evolved than actually occurred. So the change in H would be too low. So you need to be able to work out, if you altered the amount of water from when you calibrated it to when you used it, how would that affect your kilojoules per gram or kilojoules per mole?